Now I'm looking at the notes packet, and hopefully you have it out in front of you too. Please follow along. So a parametric equation for C, which we discussed last lesson, was x equals x of t and y equals y of t for t belonging to some domain. Now the vector equation for C is simply the same. We'll say the vector at parameter t is equal to the x component and the y component. So the only difference is I write the parametric equation inside a vector. Of course, t is the element of some domain. We often talk about a position vector. Where is a particle at, let's say, some time t? So the position vector, we can denote s of t, and I like to write it as r of t. And the position at parameter t is just the x of t, y of t. Remember, when I plot this vector, it's a point. So if I ask where is the particle, it's basically what is the coordinate of the particle on the Cartesian plane. Now the velocity vector is simply denoted r prime of t, and it's real easy. It's just the derivative of the x component, comma, the derivative of the y component. That gives us the velocity vector. Finally, acceleration vector is considered r double prime of t, and again, this is just now the second derivative of the x component, comma, the second derivative of the y component. Pretty easy process. Let's look at this graphically. So here is some curve. See, it does not have to be a function. That's our curve. And at some particular time, let me draw the vector here, vector r. So this would be r of t naught, let's say. And then the velocity vector is really the tangential vector. So the velocity vector is going to be tangent. Over here, the velocity vector is tangent. Each place, the velocity vector is tangent to the curve. Not necessarily orthogonal or perpendicular to our vector. It sort of looks like it was here, but you can see out here my r vector points to here, and then the velocity vector clearly is not orthogonal to it. For speed, speed is simply the magnitude of the velocity vector. So that's going to be the square root of x prime of t, the x component of the velocity vector, squared, plus y prime of t squared, the y component of the velocity vector. Okay, again, that's simple Pythagorean theorem. We could also write that as the square root of dx dt squared plus dy dt squared. You might also notice, ooh la la, that this here also represents an increment of length. Let's look at that graphically. So velocity vectors, again, are tangent to the curve, like this. But now picture taking these velocities but only having an infinitely small increment, so that light blue, all along here. And if I add up these infinitely small blue over the parameter t, then that will give me the length of the curve. This next section is the most important part of the lesson. In fact, I'm going to venture to say the most important part of the entire unit. We have differential equation method of finding a position function. We'll do that in a moment, and that's C example 2. That's where we'll illustrate that. And then there's the fundamental theorem of calculus part 2 method for finding a position function. I'd like to write here C example 3, but I want to develop it right now. So x prime of t, what does that give us? Can you think of it? It's the rate of change in the x coordinate. Rate of change in the x coordinate. It's how fast the particle is moving in the x direction. You should recognize this next expression. We've worked with it in chapter 5. What does this represent? Hopefully you're thinking this is the displacement in x. So particle moves like this. There's a displacement in the x. From here to here is the displacement in the x direction. Let's define this. Let's say that x of b, well, that's clearly the position of the particle at time t equals b, and we have t of a, which is the position of the particle at time t equals a, obviously. And then we should know the fundamental theorem of calculus in regards to this, and that's going to be leading us to that x of b equals x of a plus, so it's starting position, plus the displacement over x. Remember, the integral from a to b of x of t dt is equal to x of b minus x of a. And I solve for x of b here, and its initial position plus displacement gives me my final position, my final x position. Now these are the same for y. We'd have y prime, and they would give us respectively y displacement, etc., etc. It's time to look at some examples. Examples 1, 2, and 3 are for the notes. Example 4 and 5 are really more for your practice, and then you've got homework. This particular lesson is probably the most important lesson of the entire unit. Here we go. It says that a particle moves such that the x-coordinate is t squared and the y-coordinate is 4 minus t cubed. Let's first write that as a vector. R of t is t squared, comma 4 minus t cubed. Let's also write the velocity vector. Now the velocity, if you remember, is just the derivative of each of the corresponding components, negative 3t squared. All right. Now let's look at A. In part A, they simply want the speed of the particle at time 1. So first let's find the velocity at time 1, which is going to be 2 comma negative 3. And then the speed at that time is going to be the magnitude of the velocity vector at 1, which is the square root of 2 squared plus negative 3 squared, which is radical 13. That is the speed of the particle at time equals 1. Part B. Find the acceleration vector at time 1. Well, the acceleration vector in general is always 2 comma negative 6t. So clearly the acceleration vector at time 1 is equal to 2 comma negative 6. Okay, that's example 1. Nice and easy. In example 2, they give us the velocity vector and ask us to find some other things. So in part A, they want the speed of the particle at 3. So I'll find the velocity vector at 3, which is 9 comma sine of 3 pi, or 9 comma 0. And then the speed at 3, magnitude of the velocity vector at 3, which is going to be equal to the square root of 9 squared plus 0 squared, which equals 9. That's the speed. Alright, we're ready for part B. Find the position vector, or position of the particle when t equals 3. This is what we came here for. And we're going to use the differential equation method. We're going to use the plus c method here and explore another method later. Anyway, r of t is going to be the integral of velocity vector at t dt. And so what that is here, it's the integral of the corresponding components. This is the differential equation method. Now when I do that integration, I will get some constants of integration. I will get t cubed over 3 plus c1, and then in the y I'll get negative 1 over pi, use substitution, cosine of pi t plus a different constant of integration, c2. So I need some condition in order to solve for c, and luckily they tell us in the problem that at time 0 the particle is at 1, 0. So that tells me that r of 0 equals, well, I'm going to plug in 0. So I have 0 plus c1, and I have negative 1 over pi plus c2, and that gives me the position 1, 0. So I solve for two different c's. c1 will clearly equal 1, and c2 will equal 1 over pi. That's because I have this initial condition. So my position vector is t cubed over 3 plus 1, comma, negative 1 over pi cosine pi t plus 1 over pi. That gives me the position for time t, and then the position at time 3 will give me 10 and 2 over pi. That's using the differential equation method. That's actually doing integration by hand and finding the constant of integration, which will be different than what we do in example 3. Similar to example 2, in example 3 we're trying to find a position vector. Okay, now let's discuss why we cannot use the differential equation method. If you try to integrate e to the radical t minus t, you will find it's not integrable. So there's no way to do this by hand because you can't find the antiderivative, you can't find the value of c, so there needs to be another way. The same is true here. The integral of the sine of radical t plus 1 is not integrable. There must be another way. This is a calculator active question, as are most of the questions in this particular unit. So what we'll do here is we desire what is the position vector at t equals 4. So at t equals 4 we want to know where is the particle. So we want to know x at 4, we need to know the x component at 4, we also need to know the y component at 4. The x component at 4 considers where do you start? Well, where does x start when time equals 1 using this condition, plus the displacement in the x, which is the integral from 1 to 4 of x prime of t dt. And of course the x prime of t is right here because it's the velocity vector. Okie dokie. And in the same way, we will say what is the y position at 4? We consider where we start, y at 1, plus the displacement in the y, integral from 1 to 4, y prime of t dt. That comes from here. All right, now how do I do this? Well, it's calculator active. This is going to be 2 plus the integral from 1 to 4. Perhaps you have typed in this red equation into your calculator as y1, and I'm just going to repeat this here. So this is e to the radical t minus t dt, and I'm going to do those operations, and it comes out that it's 9.278. So that's the x coordinate at time 4, and then the y coordinate is going to be -3. See, here's my starting x and my starting y is -3 plus the integral from 1 to 4 of the sine of radical t plus 1 dt. That value comes out to be -0.200, rounding to 3 decimal places. So the answer to the question, where is the particle at time 4, or what is the vector, position vector at time 4? They answer the same question, 9.278, comma, -0.200. That answers part A. Part B. Okay, this says find the distance traveled by the particle. That's just the length of the curve from 1 to 4. So the length is going to equal the integral from 1 to 4, the square root of x prime of t dt plus y prime of t, each of these squared, the sum of them. And since these are already in your calculator, this should be a little easier. And this is going to come out to be, actually, you know what, let me just write this out in case you have any hesitation of what these values are. E to the radical t minus t quantity squared plus the sine of radical t plus 1 squared dt. Oops, I forgot my dt over here. Compute that in the calculator and we get 7.828. That is the distance traveled by the particle from 1 to 4. I would also like to note that example 2 could be done this way also. Now, I would like you to do example 4 and example 5 completely on your own. But before you press pause, I would like to talk about it a second. Example 4, just have at it. It's a calculator active question. Example 5, no calculator is allowed. I would like you in example 5, part B, where it asks for the position of the particle at time 3, I would like you to do it 2 different ways. Again, example 5B, I would like you to do 2 different ways. The first way is do it using the differential equation method. That's where you solve for the constant of integration. And I would also like you to do it with the fundamental theorem of calculus method. Both of them can be done without a calculator. Please do them both. Press pause now, because when you come back, I will be talking only solutions. Here is part 4A's solution. Now, where did I get the 5 and the 4 from? Where did I get the y of 2 and the x of 2 from? That came from the initial condition. When t equals 2, the coordinate is 4, 5. For B, the speed was 2.275. For C, the total distance, which is the same as the length from lesson 1, the integral from 0 to 1 of the expression seen, the answer is 1.458. The answer to 4D is the coordinate 3.954, 4.906. The only way to do this problem was with the fundamental theorem of calculus. and the calculator because the components of the velocity vector were not integrable. Moving on to example 5. 5b using the differential equation method is seen here. My values of C1 and C2 were 0 and 5 respectively, and my final answer is here. I'm now going to show 5b using the other method. And here it is. Now, I always prefer to do the method in yellow, the fundamental theorem of calculus. I prefer this method because it always works. This method up here only works when it's integrable. You decide what you'd like to do about that. And here are the answers for 5C and 5D.